Okay, good evening, everyone. It looks like we are live now, almost on time. I welcome everyone to this first session in that format, which is a guest lecture online hosted by the Chair for Digital Methods and Architecture at the Leibniz University, Hanover. So, did you have any problems hearing? Was there feedback? I think there's something. Okay, fine. I think it's just on my side. So just a second. Okay. Okay, I would just speak over that. I think I'm hearing myself twice. I'm ignoring that. I think for everyone else out there, it is working well. So the format for tonight will be that we have Vasily Sitnikov, who will introduce in a moment. In addition to our guest tonight, we have Johann Bettum, director of the Städelschule Architecture class in Frankfurt, where Vasily also spent some time studying. So we have Johann in here, and we have Victor Sartenberg here, who is a researcher at the chair here in Hanover. The three of us will be having a conversation after each of the three acts of tonight's lecture by Vasily. So there will be Q&A in between. For everyone out there on YouTube, you are invited to comment on the YouTube comments, and we will try to include your comments and questions in the Q&A sessions after each act of Vasily's. So yeah, please use the comment function so we have kind of as much as possible interaction in this kind of online format. So that is the kind of technicality of tonight. Each of these acts will kind of last for kind of 15 to 20 minutes. And let me introduce our guest. Vasily Sitnikov will talk about ice formwork tonight. Vasily is currently finishing his PhD dissertation at KTH School of Architecture, Department of Architecture Technologies in Stockholm. The thesis is supervised by Professor Oliver Tessmann and Professor Tim Ansey. Vasily is a Marie Curie Fellow and member of the InnoChain training network. It's a EU-funded training network which is set out to foster architectural research in linking up academia and practice. Vasily is conducting a major part of his research with a practice partner, Vero Happold, in London. Together, they've published several papers on in architectural formats, in engineering formats, as well as material sciences. So it covers quite a large area. And Vasily will go into detail of his kind of dissertation work. Previously, he was he graduated from the Moscow State Institute of Architecture, and later on went to get a Master of Arts in Architecture degree from the Städelschule Architecture class in Frankfurt. He also worked a while along with Thomas Saraceno, specifically on the early parts of Thomas Saraceno's Erosion project. So I'm very much looking forward to see Vasily's lecture tonight, as that that interest, or kind of the experiment part of his research interest, was initiated back at the Städelschule, and it's kind of developed, kind of quite matured now in the last 4 or 5 years. And I'm really looking forward to see Vasily present and having a kind of engaging conversation in between the parts of the presentation. So Vasily, the stage is yours. Please take over.
Hi, hello everyone, and very happy to be here presenting. Thank you for inviting. I think it's going to be an interesting conversation, considering the honorable mentioned members of our small chat here. So my presentation today would under title Applying New Production Philosophy to Digital Fabrication of the Bespoke Concrete Element is basically overarching the scope of my research during the 4 years, which was dedicated to production of new forms of concrete elements or concrete designs involving both new types of concrete, which show more and better environmental performance, and also new material systems which enable these materials to be processed industrially on an architectural scale. And particularly, I'm talking about the use of ice as the formwork material, as an attempt, and basically the research in this direction was an attempt to study and document the effects on environmental aspects and economical aspects and social aspects of production of geometrically challenging concrete designs. So I would start by, basically the conversation today will be divided in 3 parts, leading to methodology of my experimental work. The first chapter would be dedicated to pinpointing the aspects of concrete sustainability in the global scale, speaking of energy intensities and greenhouse gas emissions caused by this industry, trying to map out how the concrete sits today and what are the most promising ways to reduce its environmental footprint. The second part would look into the state of innovation in the concrete production, how concrete industry has adopted to use of digital means of fabrication, and how architecture is gaining new means of expression through those techniques, and also nailing down the environmental effects of these new techniques, like how do they perform, what energy, what labor intensities do they still require, and kind of on the consumption of this mass research data. I would build an argument for ice formwork and how this thing has proven itself during the experimental work conducted in the 4-year research. So without further ado, I will go to the kind of historical mapping of environment conscious approach to concrete. And the first thing to mention here is that the history of environmental assessment of concrete is quite short. So while the whole concept of sustainability grows from the physical definition of greenhouse effect, which was published in 1903 by Svante Arrhenius for the first time, the environmental aspects of concrete were still unclear until maybe 70s or 60s, when the first concepts of life cycle assessment came around. And in general terms, the life cycle assessment is a form of accounting for all the material processes and emissions that are caused by an industrial process. So it was developed in order for scientific community to be able to compare two products, not only based on their economic performance, but also on the basis of what actually they have contributed to the consumption of energy and emissions of greenhouse gases, right? Throughout their lives, spanning from the very production of their raw materials and leading down to recycling and possibilities of reuse and the lasting of a product. So this concept is crucial for environmental design, which is becoming more popular today or spread all over the society as the reaction to the development of the discourse of sustainable development, which starts from 1987 when Brundtland reports funded by United Nations have first alarmed the upcoming hazards for the society, right, in forms of both or thrice environmental, economic, and social. So sustainability tries to build strategies to stabilize the direction of all of these three aspects. However, in concrete, and particularly in concrete, in cement construction industry, the first life cycle assessment took place only in 2012. So it was lagging behind other industries for quite some decades. At the same time as founding of Global Alliance of Building and Construction has only took place in 2015, which means that even though there were attempts to look at the building industry from the environmental perspective, the actual construction part of it was missing out for until 5 years ago. The reason for lagging, which was just addressed, is basically the immense complexity of the processes and industrial material flows that support construction processes. And even though cement industry was kind of easy to address early on, because cement falls out as a very big chunk of source for both energy demand and emissions of the greenhouse gases, to build a comprehensive understanding of what energy and materials go into one building was kind of an impossible task before digital tools came around in form of building information modeling, which was also quite recently, like 10 years ago. So even though, as I've mentioned, the cement was understood to contribute up to 5% of the global greenhouse gas emissions early on, the actual gas emissions of the construction processes were nailed down, or like were basically first time calculated in 2018 and published in the first report of Global Alliance of Concrete and Building and Construction in 2018. And this paper has basically brought light to the fact that 11% of all global gas emissions come from construction processes, in comparison to 28% of operation related emissions in building industry or in built environment broadly. And this kind of conflict between the two is pretty obvious because for many decades, many governments have been trying to reduce and optimize the use of energy in buildings as they operate, right? So to build more efficient heating systems, cooling systems, or introduce what is called like green energy generators, such as solar cells to the building as a machine that would support itself with the energy it produces. However, the energy that went into construction of these solutions was kind of overlooked for some time. And recently, basically a heated debate started between different authors who take sides on whether standard new houses are actually more efficient in the life cycle perspective than a passive house, basically because the second would use much more energy to insulate the walls and provide all the infrastructure for the system, for the energy efficiency for its life. So it builds up a very high embodied energy in a building solution. And then, of course, more complex, more energy intensive materials are sometimes more difficult to recycle, which also kind of reduces its life cycle performance. So what is better is kind of unclear at the moment, and it really depends on the case, because the buildings take place in different environments, in different climates, and every single approach needs to be understood in particular. However, it became clear that embodied energy is just as important as the operational energy in the attempt to achieve a more sustainable building sector in general, and not just to shift the energy from one sector to another. So looking down to particularly concrete industry, one needs to also understand that concrete is a composite material that consists of different raw sources. So these are cement, aggregate, and steel for reinforcement in large. There are also smaller parts of materials such as fiber or various additives, but they represent a very small part of the composition. One can see that cement is the most environmentally important material of concrete, even though its total volume is much less than aggregate, and even though its energy intensity is much less than steel. So this was easy to understand very early on, maybe in the 70s, as soon as you just look at the chart of the components used in concrete. So there were taken and developed quite advanced strategies to reduce amount of cement in concrete to make it what is known today as green concrete. However, with less cement as a major binder in concrete, the properties of the material reduce. You will get a more porous material with less strength, practically, and these effects directly impact the durability of material. So by reducing the cement, one would make a green concrete, which actually would last less, and therefore compromise the life cycle performance. So very recently, there was an alternative pathway for developing a sustainable constructions of concrete based on ultra high performance concrete, which is a new grade of this material. It involves a higher concentration of cement in concrete, but it gains drastically more dense structure. And those lead to material savings because the material is much stronger and lasts for much longer time. So to understand this in particular, one needs to take a look at a specific construction type or application of these materials in relation to, for instance, a column. So in order to fulfill a specific structural task, such as supporting 3 tons of load, one would need 240 I'm talking about per meter of column, right? One would need 240 kilograms of C30 concrete, making a column as thick as 10 centimeters. With ultra high performance concrete, the thickness would drop down to 25 millimeters. And even though this second column would have a much higher concentration of cement, the actual consumption would reduce almost twice. So this was one of the latest developments in the material science of concrete. And the argumentation is quite difficult to argue with. However, a slender column like this would not feed any existing standards, would not be directly fabricatable on the existing infrastructure, because basically the tolerances for such a slender construction require to be much higher. Which leads to basically the second part of this talk, which is how does industry of concrete preparing to meet these structures, the new type, and basically reinventing the ways we build elements of concrete. Of course, with use of digital fabrication tools and new materials for the formwork and how it all sits together, right? So we can have a clarifying questions at this point, just to make sure that I have not slammed through some of the topics. Or everything is clear so far. Everybody's mute.
Everything is super clear.
Super clear.
Super clear. So these are, but you're basically reporting on recent research, past and recent research with respect to for the concrete industry, right?
That's right.
Yeah, this is not necessarily research that you have been conducted, for instance, together with Bureau Happold or anything.
Yeah, well, Bureau Happold is a structural office, right? Structural engineering office. So our collaboration with them was more directed towards particular designing of a prototype, or
yeah.
Also it was my first interviewing body that helped to identify what is actually missing on the construction market, like what applications are there to develop further.
Mm-hmm. But so I'm also curious about one thing. I mean, it's a long time since I spent time looking at material and material systems. But one thing, and you know, Vasily, that was largely in fiber and textile reinforced polymer composites. But so one thing that was like the key phrase at the time, or like returning sort of interest, was basically life cycle analysis. And I always had the impression, and I think I'm guilty of also having used it myself, but I always had the impression that it hadn't come very far at the time. It was a very obscure and relatively imprecise system for modeling. Has that changed? Do you think it is precise right now? Because you use it also quite a bit.
Well, I do refer to it, and I do study what is going on today in this area.
Mm-hmm.
So what I have kind of came to understand is that with the use of building information modeling, with managing like non-human amounts of data today, life cycle assessment can become a practical, precise tool.
Mm-hmm.
Because of course, prior to any digitalization of this calculations, yes, it was very general. These estimations were basically quite often out of the blue, right?
Yeah.
So I think in the next decade, we would see development of building information modeling, built-in solutions for like simultaneous calculation and estimation of all the major values related to the life cycle assessment and kind of environmental footprints. And as far as I know, these developments already take place. It's just the matter of when they will kind of come to a quality that it is integratable into every single project made in BIM, right?
Yeah,
I think we're on the way there.
Yeah. Because I suppose also it's soon a question of how inclusive such a life cycle analysis model would be. Like how many things to take into account. I mean, one thing would be the trajectory from natural resource to waste material and reuse of that waste material. But what about all the other aspects, such as, for instance, so with polymer composite materials, or precisely material systems, one argument was in fact that it, being so much lighter than other material, alternative material systems for construction, it is far less a burden on inner city environments during construction period. So, and basically also spares human lives in terms of health and injuries in terms of transport and moving on the construction site. So, I'm just pointing to one possible sort of dimension of what could also be included in life cycle analysis. And I'm not necessarily asking you if you know if that is being now practiced. All I'm pointing to is that, I could imagine, and I wouldn't be surprised, although I'm speaking from ignorance, I could imagine I wouldn't be surprised that it's also very soon as some result is being presented with respect to life cycle analysis, that result could also easily be challenged due to things that may have not been incorporated or other sort of forms of adjacencies with respect to material use, consumption, but effects on everything from the built environment, noise levels in the city, and so on and so forth. So.
Absolutely. I mean, I totally agree. It's what you're pointing out is the kind of a philosophical critique of whether life cycle assessment can ever become comprehensive, like a kind of a virtual model of what is actually happening and taking place in all the relations, right? In all the kind of complexity of the networks involved, different actors. Yeah, I mean, I think it's very inspiring and kind of provoking topic. Like, can you really account for the distance every work goes to the production plant in every construction? And the means how they get there. Is it by car, by bike, by underground? Yeah, I think the discourse it really creates is something new. And, considering that building information modeling became common architectural subject less than 10 years ago, so to say, like architectural design has published like the first compilation of papers where people like Greg Lynn reflected at this phenomenon. I think it was 2012 or 2008 maybe. It was quite recent, but the tempo of development is pretty steep. So I would say pretty soon there will be more digitized data to analyze.
What I find interesting is that you point out that the kind of assessment or life cycle assessment of concrete is quite recent, and the entire building industry is kind of lagging behind. And I think Johan's question, how kind of reliable or serious that these studies and data is, I assume we can trust them quite well, because there is a heavy interest by people who see, let's say, carbon emission taxed in the near future. So the moment actual overall energy consumption will be priced differently based on carbon emissions, first of all, policymakers want to put the price tag on that. On the other hand, industry wants to know what is the most efficient way to build products. So I think that's why we suddenly see this kind of research coming, and I quite trust the data, or it's kind of developing, but I find it really interesting. What comes to my mind when I see you presenting that is that actually concrete hasn't really been developed as a material system much over the last 80 or 120 years. It's just starting now as these pressures mount to kind of actually go through some technology changes. And I think you pointed out quite nicely with the comparison of standard concrete and the UHPC column that you can take the same load with just a fraction of the material. And at the same point, you're pointing out current codes won't even allow for that type of construction. And I think one thing is kind of life cycle assessment is kind of doing their homework because of the Brown measures. And the other part which has to follow somehow is policy making and code formulation of building codes. So I think that is something super critical. And yeah, maybe you can show us more of that in the next chapter, how these findings actually weave their way into practice.
Exactly. Yeah, I'm happy to continue with the retooling of the concrete industry and the forms in which the industry needed to develop new ways of making things in order to meet architectural demands. So what I've been looking in is basically precision processing of the formwork, that is the digital means of fabrication in form of CNC milling of the formwork that has been used in order to build a specific project. The projects were quite often already designed, so the solution needed to be prepared in a very short time. And in this kind of biased situation, you actually see that the solution could be developed much better if there was like a long-term research in that discipline, leading to an optimized solution. However, we have what we have, and I'm looking into like 20 years of using digital fabrication in concrete. And this has appeared in 3 different material variations. So the first one is the normal reinforced concrete. So the classical concrete structures reinforced with steel, which are either made on site as an in situ casting procedure or precast on a prefabrication plan and transported to the site. The second type of concrete used in these applications is glass fiber reinforced concrete, which suddenly allowed to reduce the weight of the elements, which are often just cladding. So you'd like to have them as light as possible. And this has been around for quite some time already, but with digital tools, it became like actual again. So this is one of the interesting findings of the research. And finally, I'm kind of shedding some light on the emerging field of high performance fiber reinforced concrete in digital production. So to begin with, in situ cast normal strength concrete appeared in the early 90s. And in most cases, it is basically an integration of digitally prefabricated parts with the existing standard fails work on site. That is constructing the whole formwork and then monolithing it with concrete on top. The cases of this project using these techniques is quite vast, and it spans from 1998 Gary projects, and here is one by Amanda Levitt in Dublin, which is a Spencer dog bridge. And you can see that all of these prefabricated elements are basically polystyrene foam coated with polyurea. and yeah, brought on site and assembled manually in chunk, like in a continuous surface. However, you can also, having a person next to it, you can understand what volumes are we talking about. We're talking about thousands of cubic meters per one project, which sometimes exceeds volume of concrete very many times. So one of the early implementations was in Gary project in Düsseldorf. And one can understand how complex it is to assemble something of styrofoam on a construction site, where all the elements are like a puzzle you need to find and fit. So it requires a lot of manual labor. At the same time, there are always problems working on site, which are basically related to the weather conditions and the general management of the waste material, like making sure nothing just flies off with the current of wind. So quite early, this production technique have moved indoors in the form of precast normal strength concrete. This approach was also used in Gary's Nordzollhof in Düsseldorf, where hundreds, if not thousands, of elements of unique shapes were using single-use EPS formwork, and then pretty simply manually shaping the backside of the elements, because the consistency of normal concrete allows kind of manual sculpting. However, let's just pay attention to the also amount of waste material that this approach causes, as well as the amount of pretty not nice manual labor that needs to take place. Though the performance of the method was proven very efficient because you have a very high tolerance, you have really high automation level if compared to a normal kind of plywood assembly formwork. So the method went pretty popular quite soon, featured also in this Trahan Architects Louisiana State Museum in Louisiana, where basically a different version of concrete, but also similar properties, but different version. It's called dry cast concrete, have been used for the cladding of the interior surfaces of the hall, where you can see that in this case, you would already need a advanced coating of the formwork, as well as more complex assemblies, as here at the back of the workshop, there is pretty developed volumetric formwork, but still relying on manual crafting and kind of compacting of each of these elements manually in the formwork. At the same time, all those cast concrete elements are imposing a great dead load on the structural of the building. So there was always the intention to make it light, right? To reduce the mass of the structures and keep the free form geometry in the design. So with these intentions, the glass fiber reinforced concrete has gained a very high popularity. Basically having one digitally made formwork, one would just apply this very thick concrete saturated or the concrete with a very high content of fibers by spraying on the formwork, which is autonomously providing this very thin shell instead of a volumetric cast, right? So this approach was used in the wheel of the Broad Museum by Dillers Cathedral Renfrew. And you can see in this diagram also how, even though the elements look same, how different they are and how many versions of those there are. Depending on the program of the building, on the structure behind, on many, many aspects, the geometry of an element changes. And that means that you cannot use one universal mold for all of the elements, which also leads to use of EPS formwork, because it's the cheapest and the most affordable, fastest to process material. However, the properties of glass fiber reinforced concrete are not quite superior. So it cannot really carry itself. It requires additional stud frame at the back as a form of external steel reinforcement for either processing, maneuvering it on site, and installing. So it does come with certain limitations also in the surface quality, because in order to make an element of architectural design quality, one would basically need a very skillful labor, right? It's not already just kind of shaping the backside of the element. It's practically a craft. The same project, the same technique also featured in the Seyon M Bridge by Morphosis, building that is about to be finished. And you can also see with these diagrams how complex the building envelopes become at this point, like how many layers there are, how technical and basically futuristic they are. And still, how many elements need to be produced to cover all the surface of a building. And in this case, the elements were made in another country, so they were actually imported from China to Korea in order to, construct the project. So there was also another parameter which had to be considered, which is the shipping size of the element. And here you have the diagram of a container that is a 12-meter container, which fits 4 of these facade panels at the same time, right? And so because they are very thin, they are quite light, and one container could actually carry 4 of these elements, right? Even though the limit to it is kind of at 1 ton. The practical drawbacks, however, are still that the formwork needs to be crafted, right? So it has to be made for each element, because sometimes the geometry does not allow reuse of the formwork. So there are certain constraints that are staying with it. Still, the fact that it is not anymore a solid stone, but just a shell of an element, pushes the performance quite high. And here we come to the concept of the ultra-high performance concrete, which is basically capable of doing the same shell. However, its superior physical properties does not require the external steel reinforcement anymore. The concrete element can start to perform on itself, even though the thickness would be 2 or 4 centimeters for a giant facade element. However, the properties of this material in a fresh state required development of new approaches to making the actual product. So you cannot anymore spray it, because it requires, like, it is a self-compacting concrete. It requires flow ability in order to make the dense structure. So one of the devised technologies was based on an adaptive mold, which is a element is cast flat on a table and let to set for a while, so that the thickness reduces or increases the thickness, so it does not flow anymore. And then the table is bent into shape to meet a particular facade geometry. And the technique was used in 2 quite outstanding projects, which is Gary and Partners of the Foundation Louis Vuitton and the UN Studio Arnhem Terminal. So both projects, I think they won some kind of prizes in terms of efficiency of concrete, because the facade cladding in both cases was extremely thin, like 2 centimeters without any extra supportive structures. However, this method, of course, would not account for all geometries, right? It is only applicable for kind of smooth curvatures, and would not really respond to any creases or more aggressive designs. So for casting a more versatile geometry, there was another approach, which is a more complex formwork system consisting of a mold and a countermold. So having like control over the both surfaces on the back and on the front, one can actually make a very high tolerance, ultra high performance concrete. Such as in the case of Mall of Netherlands, built recently in Netherlands. However, for such a formwork, you cannot anymore rely on styrofoam. So for this project, a lot of MDF stock material was used and CNC milled in order to constitute a kind of a more robust formwork solution, which would comply with the very narrow tolerances required. Which is a bit of a problem for the budget because, well, volumetrically, MDF is way more expensive and carries way more environmental effect than the styrofoam, which is on 98% constituting of air, right? So overviewing this concept, or industrial methods used today in the practice, one can notice that the major problem with them is that they use non-recyclable material for production of unique products, right? So to every concrete element, there is a ghost of particular volume of polystyrene or particle board that has been just wasted in the production process. And of course, it is hard to track this. However, it carries specific environmental impacts. It increases the embodied energy of the concrete element, as well as its carbon footprint, and so on. So at this point, realizing the impracticality or like inefficiency of these methods, a lot of universities studied ways of development of recyclable formwork for concrete. And the most prominent is the industrial wax-based formwork, studied both by Osterle and by Meinke in Zurich and in Germany, Braunschweig, I guess. The problem, however, is that in the context of concrete, it is very difficult to recycle something when you have a lot of sand, you have a lot of dust around the formwork and in the production. So it's kind of a messy production, which constrains the recyclability of materials such as wax. At the same time, wax is very energy intense and extremely energy intense, in fact, and quite expensive as well. So in order to get to the performance of EPS, you would need to recycle the same volume of wax for at least 100 to 100 times until it gets equal, right? Beneficial. So one important project that was done for my research within my interests was the project by Gericke in Stuttgart, who basically studied the use of frozen sand as the formwork for production of concrete. So in this case, the kind of moist sand was frozen to a solid state and then CNC milled in order to cast concrete. Their research, unfortunately, was discontinued in 2017, but having some papers published, I came across and I was quite inspired by it. I think using a local material as the formwork material that also can go through practically unlimited cycles of freezing and thawing, one can actually reduce, completely cancel out the energy and environmental kind of impacts of the formwork material, leaving concrete to perform on its own in the environmental sense. Right, and here we come to the beginning of my methodology for developing of this approach. And we can also, of course, have some questions if you like.
I started with a question coming from the audience, actually, and it might have applied more to the previous chapter. It came in quite late, but I'm still reading that out. It's asking whether the geometry and the form factor and flow of forces, if that's even more important on the overall energy consumption and carbon footprint than the actual material being used. So whether structure engineering goes over material science in a way.
Can you rephrase again? So is it the question of whether the formwork is more energy intense than the material itself?
No, I think the question is whether the structural design, the layout of the flow of forces is more important than the improvements on material performance.
I mean, I would say definitely with tools such as topological optimization, one can drastically reduce the use of material. However, there are other functions that elements carry, not only structural, right? So I think there always will be the problem of imperfect design that needs to be produced. So in a way, something that has, I don't know, function of an aperture or function of a on the other hand, it can be a separation wall which needs to be solid, right? And then topology optimization would produce on the opposite something that is open and porous. I think it is definitely, it has to be integrated into design at any stage, because of course we need to save material by precisely calculating forces in an element. This is beyond discussion, right? But there will always be design that is not that you cannot really absolutely optimize.
I think, I don't know when the question came in, but I think you made a clear point already with the straight column. It's like a straight column, that's the most optimal flow of forces you can have. Yeah. And you can still do a lot of improvement by using a high-tech material just as UHPC. So I think.
Can I add to that?
Please.
Yeah, because I think no. I think to me the answer is no, for a very simple reason, and that is that, you know, I think that over so many decades now, if not more, the emerging lesson is that we need a greater holistic way of thinking. So there is no in architecture, there is no such thing as a material without a material form. And the moment we have a material form, for whatever purpose and application there might be, that is already geometry and material makeup. And, you know, it's a very, I think it's a very simple, you know, difference between a sheet of glass and a concrete surface. When it comes to geometrical articulation and the possible then assimilation of flow of forces and the distribution of those are obviously so radically different that it's almost impossible to even compare. And maybe that was an absurd sort of pair of materials, couple of materials. But I'm also intrigued, Vasily. I mean, of course, many of the things that you speak about harks back to things that I spent time looking at a long time ago. And again, to repeat, with respect to polymer composites. So to me, I was always fascinated with Frederick Kiesler's formulation of co-realism and biotechniques. This was way back in the late 1930s, where basically there was an attempt, however naive it may have been, but to see, you know, that that we as humans, we need to have a more, we need to be greater in touch with and integrated with a broader context of materials and material use, but also eventually with respect to aesthetic effects. And I think that with very many of these things, there might be the difficulty of life cycle analysis, as pointed out after the first chapter. But right now we're really at sort of conundrum of considerations that pertains to architectural design and the construction of buildings. And it's enormous, and it continues to be a wonderful, wonderful challenge, I think, where industrial practices and resources and practices needs to be wedded with, architects' ideas of particular formal effects of what they design, and into that economy of variables and into that economy of considerations. I just don't think it's possible to at any point give priority to one thing over another. So, to repeat, I think that the geometric form of any material element or any architecture per se needs to be specific and specifically wedded to, an idea about what effects one wants to produce. And then, of course, that comes hand in hand with the very, very specific material application, material choice and its application. There's another thing that I thought about too. I mean, so much, and forgive me then for being also using history here a little bit, but so much of what you show also makes me think of the early practices with ferroconcrete. So this is my lab with the bridges in Switzerland, such as the Schwanbach Bridge, also I think early 1930s. And one of my favorite projects ever was the open flexible mold that Renzo Piano Building Workshop developed. I think it may have, I'm not sure whether it was actually called Renzo Piano Building Workshop at the time. But anyway, it was Piano and colleagues. And that they developed in 1969 for the Italian pavilion at the Milano Triennale. And it was flexible. It was basically adjusted with hydraulic pistons, and then allowed for some of the same outcome that you have exemplified with some of with the open mold, at least the flexible open mold that you showed. Which, to some degree, I think it's a twofold sort of celebration of architecture I'm trying to make. It's so many of these things that continue to be pressing challenges and comes with so many questions, and is now also not the least wedded to increasing demands on how we're thinking about the environment and the carbon footprint and so on. That is actually also there's an outline of some of those engagements in architectural history, which I think is a reason for celebration and also a reason for not to be sad about how long it takes, this being whatever, more than half a century later, and we're still dealing with some of the same challenges. Because in fact, we have an emerging technology that may actually make some of these things accessible and practical, which I think is very exciting.
I totally agree. I think the reference you've made with the Renzo Piano formwork system, that is absolutely the same thing as the adaptable formwork that I have featured. Mm-hmm. The only thing is that it was not digitized, right? You had to manually set up the curvature. But yeah, it totally fits within this thing, and that is another proof that the concepts are having histories, right? They're developing from early. So should I continue with the second section or third section?
Maybe just one last question. Yeah. I think there's a great overview of techniques that have been developed. Surprisingly, they're mostly been developed in practice, as there was kind of mounting project pressures, let's say, to realize a given design for kind of within a budget, within a time, So these things have been developed, and you pointed out one or two examples, and one particular from Stuttgart was saying that was a design, that was a technology that was developed and published, but then suddenly kind of faded. Could you maybe say something about your findings of new technologies, whether they've been kind of developed in pure research and whether they are being developed in kind of applied research for a particular project?
I think exactly. So most of these technologies are being developed after the tendering of a project construction, right? So it's kind of a gamble. People just go and say, okay, we'll sort it out with this budget. And that's how it started in the 90s with actors such as Jerry Koo, who was one of the first to build challenging projects of Zaha Hadid and Morphosis as well, who was also architect, engaged, involved in this thing. So I think the projects we show today is in mass. They are basically these ad hoc developments on place. So there is no discussion of the environmental performance when you have 2 months to develop a technology. There is only budget feasibility and technical feasibility as well, right? So it should work, and it should work within this amount of finance. However, what happens in the universities often follows another objectives. So people are questioning things that are related to environment at a first hand or quite often. And from there, yes, the project that I have referred is one example where Werner Sobek decided, and his group decided to develop this technique of using local materials, right? But for the same reason that it is not attached to a particular commercial project. These projects come and go. Whether a situation changes in the group, then is dropped, and somebody else picks it up in another university. So that's how concepts, I think, mature to a state when they meet a practical implementation. Before the practical aspects, I think they're just kind of flowing around. And I think it would be good to have a more focused work on this, to have a dedicated effort in order to sort it out once and for all. At least to get it to a level when we don't need to waste thousands of cubic meters of styrofoam in order to cast hundreds of cubic meter of concrete. It's kind of a biased situation.
Yeah. I think it's nice how you point that out and how you make that clear, that there is this kind of mixed reality of, let's say, projects being kind of developed ad hoc in practice, although they've been then seen as kind of professional developments, although they've been kind of almost been made up in a kind of makeshift kind of development, and academia projects which are sometimes more regarded as amateur projects because they haven't been applied to a kind of to a costly building yet, but still they have quite a kind of fundamental kind of agenda and findings coming with it. So I think kind of amateur and pro is kind of mixed up kind of in a really weird way comparing these two, and I think it's good to kind of sort that out. And I kind of appreciate you kind of pointed at that already in your introduction, and kind of also finding these jewels like the Sobek work, which you say that is important, and then you start your development from there. Yeah. Okay, then let's go to the last chapter.
Okay. So picking up from where I left it, basically on very early stage of my research, I decided to focus on feasibility of casting concrete in ice, considering that there are certain inherent benefits of using this material for production. So this kind of benefits included, first of all, the recyclability of water. That is, water can be indefinitely refrozen on site in the production cycle. The other aspect of the benefits is that the formwork is self-demolding in a way that it can be melt around the complex geometry of the concrete element that is already hardened, which is a big issue in construction of complex geometry elements, because in most cases it would lead to kind of manual extraction of the formwork material from the element. Another aspect is that basically, yeah, it is based on only on energy spent on time during the production process, and it does not involve long distance transportation of water or industrial processes that come with it, right? So it's a localized use which can be powered by, I don't know, renewable sources already today. So with this having formulated in the form of a thought experiment, which is this kind of general preliminary argumentation for the system, I have defined three major steps that need to be done in order to validate the technology and kind of define its general performances. So the first issue, of course, is the hardening and contact of concrete and ice. So most of the most conventional understanding of concrete is that it is not hardening under 5 degrees Celsius. So, and this is true for major normal concrete grades with steel reinforcement. However, for concrete that is not even standardized yet for ultra high performance concrete, this law is not anymore applicable. Yet it is a new material and not many research has been carried out in this discipline. So basically my first phase was to conduct material tests of concrete and find the combination of chemicals that would help it to cure at sub-freezing temperatures. From there, I picked up the prototyping and trying to envision the production of concrete elements using ice. What form would it take with all the digital means we have today? And the final stage was the evaluation of environmental performance conducted on top of the prototypes. So the prototypes also helped to collect data in order to estimate what energy consumption it would require. Because in general, I had no idea how much energy a refrigeration of industrial level would use, right? So with the first phase, it was pretty much straightforward. The methodology of material sampling was used in order to validate, to test different samples of concrete and to catch the one that is basically hardening the fastest. And this was done even manually, like very empirically, just trying to break a concrete sample after hardening in a sub-freezing temperature. And after that, we have after I have kind of mapped out the general scope of materials that are interesting to study, I have conducted a more precise tests within the also the format of the concrete material science testing. And basically on the left, you see the blue line, which represents the hardening of HPFRC, which is high performance fiber reinforced concrete under normal conditions at +20. And it's much higher than the red line, which is representing the C30 concrete, right? So you can see the difference, how fast it gains the strength in the first days. On the right, you see the same concrete hardening at -10 degrees. So instead of having a very steep curve, you just kind of laid a bit. But then, as you see at the end, when the material is going through the defrosting phase and going out, it actually gains the same total strength as the reference sample that never was exposed to cold. So having this general finding done in the first year, I have switched to testing it with ice, right? How does it work in relation, in contact with ice? And this was evaluated very simply on the first stage by just making a cast of an arbitrary geometry. And one can see that even the very small pattern present on ice was present on concrete surface, which is basically the best result one can dream of. That is, the ice acts as plastic in relation to concrete. Yet the question of how to deal with ice appeared out of nowhere. I had no clue how to process ice, how to work with it, and what kind of techniques apply. So at this stage, I kind of studied the history, looking back on what are the practices with ice. And surprisingly, there are very picturesque photographs or documents of how ice was harvested before the refrigeration. So there was ways and there were skills of dealing with ice very early in the human history. However, with the rise of artificial refrigeration, all of this became abandoned at a large extent. However, certain cases are still remaining, and this is mainly entertainment industry. So I have studied several ice processing plants in Sweden, one in Stockholm, another in Kiruna. It's a very northern city of Sweden. And what I immediately have found is that all of these small workshops that are making ice sculptures for fancy dining basically already use digital means of fabrication. So in the small workshop in Stockholm, I found that the small CNC router was milling different or engraving different patterns on ice with the operator staying in the warm outside. In Kiruna, I found a decent industry size warehouse with kind of round year cold temperature and giant stocks of ice being handled just as if they were styrofoam blocks. So having a lot of inspiration from here, I started to develop the laboratory where I could test such ice processing in relation to concrete. And this was accompanied by publications, which you can also find on open source websites, as well as development of the infrastructure that allowed the production. So I have expanded in 2 years from 12 square meter room with a small household chest freezer to a setup which is basically 300 square meters with a industrial refrigerator being used for the production tests. And I will just guide you through this process. So the first stage was completely analog and was based on open-ended experiments based on trying to control the melting deformations of ice. And these cases were quite buoyant in terms of geometry and expression one could get. However, they were exemplifying the intensities of geometry one can make, and completely different qualities with different ways of processing ice. Basically, whatever you have in ice, you can have in concrete in the negative, right? So the first tests were based on thermal melting of ice, which is basically heating up and letting the very soft surfaces appear in ice, which are then later captured with concrete. Another approach was based on chemical melting and chemical erosion, where an ice block is exposed to chemical or salt attack, basically, and that erodes the surface in different ways. And this also produces different effects. I was just collecting, samples and patterns of design that can be produced at that point. Another completely analog approach is basically use of fused ice aggregate, which is also benefiting from the fact that ice can melt and drain away from the former completely autonomously from the concrete, releasing the concrete cast. And here, depending on the design of a particular topology of the element of the concrete, depending on the topology of ice aggregates, one can control the continuous concrete structure you can make with it. So having different kinds of ice bits, one can pretty much program what is being produced with the continuous concrete spatial structure made with it, right? So in the only process it requires is sequential melting and freezing cycles for the aggregates to fuse together to constitute a continuous ice structure, which is then drained with high performance concrete slurry. And this allows producing a very low density volume of concrete, which is still remaining its high performance qualities, having a very high surface density and very low water absorption. So it was the most interesting analog effect I have achieved, but I also needed to switch to the digital production because it's interesting how to apply this in practice. Yet this research of spatial structures has a history in my own development, and the very first samples I've made in Städelschule in 2012 were also somehow leading to the same direction. And this structure on the left later became my master's thesis at Städelschule. And now it reappears in concrete, and suddenly, hooray. So from here on, I went with development of digital process for ice processing. And here already you can see that infrastructure is expanding. I have like a set of freezing chambers that carry out different functions of the process, with the CNC mill being in the largest of them. Immediately, it was possible to test different paces of milling, of processing, and produce different surfaces in ice, and document how precise milling of ice can be. It was easy to prove with the concrete cast of the ice block that the ice was pretty sharp, right? And in fact, it was also quite easy way up because ice is very it's easy to CNC mill because it doesn't have any fibers. It's a homogeneous polycrystal that is brittle as well. So when you're milling it, it's kind of chipping and not heating up the tool, and you can go pretty fast through ice with the CNC mill, basically. So I've been dedicating time to small-scale prototypes, trying to do different surface qualities, also testing if you can merge two parts of ice, CNC milled ice into one former, making a kind of spatial object instead of just a flat element. And finally, testing the processes related to defrosting, like how easy it is to, how long it takes to melt a block of ice, right? Or to which degree you need to melt it. Can you hammer it off afterwards? Anyway, this setup was limited in size. However, it allowed to test principal chain of the production cycle. And it was time to expand. And the easiest way to expand with the sub-freezing processes is basically to hire a refrigerated container, which is a standard shipping equipment for transportation of frozen goods. So having this unit at home, I have kind of equipped it with another CNC mill, a ice production setup, as well as storage of raw materials, and the prototyping began. So here you see the much bigger chunks of ice, as well as much more significant CNC processing equipment. Everything still, the control panel is remote, so you can sit outside watching it, streaming the CNC process, having a coffee. And then also kind of larger environment allow us to test much bigger parts, not only in terms of scale, but in terms of material processing. So you can test different concrete compositions quite efficiently. So one of the first prototypes was this kind of hollow core slab. It is an abstract chunk of architecture, so to say, and it illustrates the ways ice former can be used to create deep reliefs, deep structures, and still this production used CNC milling and digital fabrication. So having several chunks of ice blocks done, they were then assembled in a kind of a bounding box to constitute a one single volume. And then they were also allowed to melt a little bit to create kind of smoothness of the surface and yeah, kind of get away from all the kind of mechanical processing artifacts on the surface of ice. And here you can see how concrete drains through all of these canals, filling the cast. And this is the cast on the right. And the interesting thing, of course, in here is that all the walls are 1 centimeter thick, even though the element is pretty large. And in order to control the space between the ice parts, and other small ice bits were used, kind of as small ice spacers, to constitute this kind of openings in between the different chambers. Yeah, and as you see, all the surfaces are blurred because they were heated in order to make the smooth effect. And finally, the main prototype in this research that is most technological, I would say, is this sample of a facade element, which is a very aggressive pattern, very sharp, based on just aggregation of extruded boxes, which has a continuous thickness of 2 centimeters throughout it. So in order to have it done, you would need 2 parts of the formwork, the bottom part and the countermold that kind of pushes out the volume of the element. And here we were testing basically bolt anchoring of the element for convenient assembly on site and aspects like that, so technical things. And here Burr-Happelt helped to also find the perfect thickness for the element. Of course, not for this prototype, but like for a full-scale project. And the second challenge of the process was to actually build this. So I would like to take you through with the film. It's a 2 minutes film. Illustrating how the production was carried out. So the refrigerator is actually quite easy to run, even though it's quite advanced equipment. So this, we just go cross equator, without maintenance. They're pretty robust. Here you can see how ices melt. First rough, and then there is a tool change. With a ball head, you get then the smooth surface finish. And even very sharp parts can be easily melted with ice. So there is no chipping effects or any processing limitations, I would say. So it's definitely much faster than milling wood or milling MDF. Correct. So here we also tested double-side processing of ice blocks. So how do you make a spatially digitally fabricated element, right? Not just a relief. And the surface, of course, can be led to also melt a bit. However, in this case, I just try to keep the sharpest geometry and assemble the formwork with the bottom part and the top part. And as you see, the top part is suspended on bolts. And these bolts are basically dipped in water and then put in the slot so that they fuse into ice and they can perform quite good structurally. And the concrete is mixed, and as I've mentioned, it's very thin element, so it requires very little volume of concrete, surprisingly. And the development of the mix basically resulted in a very workable mixture, which can feel even very complex geometry from, when fed from one side of the element, it just feels all the volumes like water would do. So after casting, there is a process of demolding, which is, as I've mentioned, autonomous. This is the time when you can go out and have some nice beer in the park. So the element is kind of matured in water, which is very good for concrete in the early stage. There is no shrinkage, the dimensions are perfect. And then there is this imitation of a construction process with welding and installation on the steel framework on the back. Basically, this is what they call lean production in the automotive industry, when you don't have any waste and everything is kind of dimensioned to fit without any on-site adjustments. So this was the product. And now, for conclusion, I'd like to mention what I could estimate of the environmental performance of such an enterprise. So basically, using linear interpolation, I was trying to estimate what would it cost to run this on a full scale, and what would it cost in comparison to other means. And since I've been using quite large equipment, I could just use the data that I have measured of the energy consumption of this refrigerator. And here I was sampling the time of the container idle when nothing was happening and it was just maintaining a stable temperature, and comparing it to the time when the prototype was fabricated. And the offset in the energy consumption would basically be assumed to be the energy added to the concrete due to fabrication. So it would be possible to linearly interpolate this data and get the results for a full-scale product. And here we get to the point where it's important to understand that depending on the design, the volume of formwork would change dramatically. So I have two large-scale prototypes, and in relation to basically, in relation to volume of concrete needed to make these prototypes, the volume of formwork ratio with the volume of formwork changes dramatically. So for this one, because you needed two giant stocks of ice for basically that fits the volume of the element, originally there was just much more formwork material. However, because water is practically the lowest embodied energy industrialized product, I'm talking about tap water. So there is nothing less energy intense than the tap water you get at home. In comparison to EPS formwork, used to produce the same element, the energy needed for ice formwork is twice lower. And this has been proved to be true for both products, with different ratios of formwork to concrete, basically. Having this said, once again, the embodied energy of polystyrene is extremely high because it comes from extraction of the oil, processing of the crude oil into special fractions, then processing further into styrofoam, then transporting it to the place processing, right? So all of this adds a lot of energy to polystyrene as the material, even though it's very light and kind of, it has a very low density. And the water, on the contrary, is reused, so you can actually just disregard it from the calculation. And this is basically the main conclusion of my research. So I've managed to construct an argumentation line of where to apply the ice formwork, like why is it needed, right? Then I managed to prove that it works in relation to particular prototypes. And finally, kind of estimate what benefit we would earn, be this employed in the real world scenario. Thank you. We can switch to a concluding discussion now.
I have to say, Vasily, it's fantastic to see, of course. I mean, it's just very, very impressive. And you will forgive me also the nostalgia of course, taking great pleasure to see something that had its birth here come to such a fruition and such a concrete result, but also a something that, you know, seems to be applicable, seems to take on various sort of levels of not only serious investments, but also possible serious consequences. And of course, Mirko, if you allow me to be a bit personal, you know, it's because you're such a wonderful, modest person, it's also should be told that, you know, this is actually took place in your studio here at the time when you were teaching here. So it's, you know, it's my compliments in that sense to both of you. It's great.
I would like to add to this because, yes, Mirko was behind this process. He was involved in a very early stage and, of course, helped me and inspired me to proceed further with the more in-depth research of the topic. So, absolutely, Mirko, I should give you all the credits.
No, well, thanks. But what I find is really interesting, kind of now being kind of distance, or only have seen the kind of initial development, or as you call it, the kind of experimentation of the project. I really appreciate how that has been developed in so many other areas, if not domains. Yeah, I mean, taking something which was kind of quite a still serious, but still kind of design experimentation. And I think that went quite far already in your work during the time at Städel. And then having the courage to kind of engineer it, to material science it, to kind of do environmental analysis on it, and still treating that as the same kind of body of work you're developing. I think that is quite an achievement to see that you can drive the project as a designer, you can drive it as a researcher, and you can also drive it as a narrator in a way. Yeah, I mean, the way you kind of narrate the story of how that could become applicable is also quite impressive to see, that you can address different audiences in a way. And I think that's where my questions would go, is like, what's the what's the response you're getting on that type of work from different audiences? What does what does structural engineering or engineering, kind of class building engineering as Biro Happold, how do they respond to it? And how does cement industry respond to your findings? We all know what designers think about it.
Okay. Well, I thought it would be interesting to know how different designers reflect to it, because I think designers are all different as well. But I would say, well, it is difficult. It is basically, it is a solution for a very niche or very specialized applications. So depending on how far a opponent or the person to which I'm presenting is from this bespoke fabrication of lightweight elements, right? This would pretty much define how the reaction would go. Mm-hmm. Yet, of course, as I've mentioned, a lot of projects, like basically what I have understood from a lot of research of the innovation in construction industry, it only takes place when the client is ready to realize an ambitious architectural or structural project. So the industry is saying, great, thumbs up, but at the same time, where is the project to which we apply it? Mm-hmm. So I think if there would be, I mean, basically what is important at this point is to spread the word, to make people aware of these opportunities. And I think only when the need is there, the industry would respond with, like, you know, come and do it here. We have a place, for instance. But yeah, I mean, generally, as I've mentioned, the industry of construction is quite conservative, and thus the response is, even though it's positive and everybody understands the value and the effect, still, I mean, it's pretty modest in terms of emotions.
Vasily, yeah. Is the result climate specific? Your specific result, that's also climate specific, right? You did this where was the large scale container? Where in Sweden was it placed?
It was in Stockholm, exactly. And from what I have studied, basically, because the process is automated and isolated in the cell, right? The containers are actually developed to such a great degree in terms of temperature loss, right? Temperature exchange with the environment, that the efficiency would not change dramatically, even if you place it in the tropics somewhere. Oh. So these containers are passing through the equator, you know. So all the avocados in Europe, we get it from South America, and yeah. So basically, the global trade industry was interested in pushing the performance of these containers long ago, and here it is, just to harvest the high-tech solution.
Yeah. Which then brings in the question of scale then. So I suppose the size of the container gives somehow, and of course the technical equipment you have, the CNC mill and so forth, that gives an idea about the scale at which it could operate. You had one slide where it looked like a huge block of ice outside the container. Is that your block of ice?
No, I think I reference here a work of what is called Ice Watch, the Olafur Eliasson project, where he placed several icebergs that he caught in Iceland.
Yeah,
it's very lovely. Yeah.
He also did a car, I think, in ice, didn't he?
Did he what?
I think he did a car for BMW in ice.
Maybe I've missed that one. I'll Google it.
Sure, and then he let it melt. So anyway, but it gives it gives an idea about scale, I suppose, which I thought is also very interesting. And what about the labor intensity? I mean, you spoke about the labor intensity with respect to certain types of certain alternative and or already tested sort of types of molding. What would be your estimate for the labor intensity with respect to your ice molding?
I would say that from what I have witnessed in my practical physical experiments, I think the ice concrete system is highly compatible with automation. So considering from the first part where ice block can be moved around basically using pumps, right, and pump system, which is bringing the water into a reservoir in a container, something like this. So I would say it has good chances to compete with concrete 3D printing in terms of manual requirements of manual labor. Yet, I mean, I mentioned 3D printing in concrete, but basically the product is very different. So there is nothing that can, I mean, no 3D printed concrete can compare with the cast concrete due to many technical issues that are inherent, right? So basically I'm trying to propose a concept for different material that is compatible in performance to 3D printing.
Right. And then in this case, your concrete, and that slipped by me, I didn't get that. Your concrete is not reinforced, right?
It is fiber reinforced.
Sorry, it is fiber reinforced. Okay, so you have small whiskers, glass fiber whiskers.
Exactly. It can be not only glass fibers, it can be also kind of stainless steel needles, which are often used, or carbon fiber. Or there are many alternatives, but in terms of again, in terms of labor, the fiber reinforcement, which you just apply in the batch, saves a lot of manual labor. And in comparison to rebar, which needs to be laid out, you know, and especially in complex geometry, the rebar or like a regular cage reinforcement, that is just a great deal of labor.
So, and that turns me also to, as you can imagine, the thing that I'm probably most interested in. You say kind of, you pretend to be sort of innocent when you say that you were hoping that you would appeal to architects' imagination in terms of design. But that would be, of course, I would probably want to turn that question to you. So then, let me give you a short example. It's very clear if one looks at, again, if you allow the example, you could take to any sort of fiber-reinforced polymer composite. There emerges gradually a sense for, emerges gradually an aesthetic language. And I'm thinking in particular that is important in terms of detailing. And the detailing example for me would be, again, turning to Renzo Piano and looking at, in fact, not that pavilion for the 69 Triennale, but I think it was 71, 72, where he returned representing Italy at, someone could probably recall this better than I do. It was a world fair. Maybe it was wasn't in Tokyo, I think. But anyway, regardless, there's a very, very distinct detailing of the fiber reinforced polymer panels that make up the entire envelope of the building, which was a shed. And I'm just wondering what sort of, without necessarily saying, you know, asking you if you've done it, far from it, but what do you see as sort of like interesting aesthetic ranges that could be investigated here, or are there any specific sort of design interest that has awoken in you?
I would say what is awakening me is the deep deep spatial design of a concrete element, right? So I'm very much looking forward emergence of this kind of pockets and deeper elements in, or deeper voids in structural and other design of concrete elements, because this is what the technology is mostly favorable for, right? I think also kind of the breaking the solid of the traditional concrete beam and opening it up, showing the spatial qualities of the structure. I think that is definitely something I'd like to perceive.
That's great. But then, with the example you now have on the screen, I mean, that would be a huge challenge to estimate the strength of that, right? The carrying strength.
It would be impossible without machine learning, I would say.
Yeah.
And running thousands of tests, definitely. But as we've mentioned before, I don't think everything should be determined as structural. I think there is place near the structural, you know, like reducing the optimization level from 100% to 90% would give you a great result, but also provide the space for making a choice, right? And making some other statements with the design. So I think this all can play together. Why not? Yeah.
No question about it, but I would think that, you know, it's basically somehow, certainly that would be an enormous sort of frontier in terms of the possible interests, I would imagine, at least on a sort of experimental level, but that is a synergy of aesthetic articulation and formal strength. Harking back, in fact, to the question that was raised earlier, you know, if not, so that was more about energy and energy consumption. And by all means, I don't need to collapse these things, but I just know that from general sort of composites, the world of composites, that, you know, it's basically the sort of coming together and the exchange of particular aesthetic forms with particular other capacities such as strength. You had that other slide up, which shows it's more sort of conventional sculptural form, but it was quite stunning. Could you flip to that?
Should I bring that? Okay.
You know which one?
Really?
Yeah, no. It was one
conventional sculpture. Ah, okay. I guess you were talking about this one.
Yes, I was.
No?
Yeah.
Yeah, this is the conventional. I totally agree.
Well, in some ways, yeah. But then, you know, starting to imagine what this could become, borrowing a little bit more from that deep, I don't know what to call it, but like the deep structural element that you pronounced your own fascination with, and seeing that, you know, it may not have to be necessarily that extreme and that porous, but basically one where you use the same sort of design agenda, but you find, and I don't think it's a compromise. I just think that, you know, it's a way of finding a language where you explore precisely that depth in the element itself, and with an appropriate type of sort of scalar articulation of voids and openings.
I would absolutely agree. I would say that what I was trying to do, and this a little bit has compromised my intentions in terms of design. So I was trying to create the palette of expressions one can produce with the concrete and ice, right? So I could have instead just focused on a particular design and take it out, but I wanted to really kind of picture the landscape of what are the opportunities, right?
Yeah.
Yeah, there are two questions from the audience. One is from Adam saying, thank you, Vasily. Very interesting research. One question. do you see there any possibility of higher resolution multi-point forming systems that would be able to achieve creases, etc., being deployed in the near future?
So this is back to the adaptive formwork, I guess.
I think, or yeah.
So kind of
I can imagine. Yeah, imagine what creased surfaces means. Yeah, maybe that's my interpretation. Adding to it, would you see any, let's say, hot wire, hot blade cutting techniques being applied to these ice blocks?
Okay, so if we go that direction, then sure. I mean, it's not a hot wire cutting, because basically with ice it is impossible to cut with a hot wire, but it is instead a thread saw milling, or thread saw, which has been featured already. I mean, there are certain design projects where this has been done, and sure, yeah. I mean, this approach would dramatically reduce the time of producing the geometry, while of course limiting the scope of geometry with the kind of ruled surface based approach. Interesting, but perhaps.
And there's another question saying, Vasily, where are you going to set up your business? Are you planning to ship the concrete objects or the fabrication units all over the world?
To ship the projects, the products, or the fabrication units. I don't know. I mean, I'm so far from starting a corporation yet. A holding, maybe a holding first. But definitely everything is possible. I mean, you can have it in Antarctica, you know, without any refrigerators. Then you would just ship it with the I don't know, autonomous boats, which are just following a current in ocean, and arrive to Venice Biennale just in time.
Yeah, I think that part of the calculation is probably relatively easy to decide where it's better to ship the container or the product, depending on the location where you need it. Okay. I think we've almost taken up 2 hours. I very much enjoyed your presentation. I enjoyed the presentation, the discussion. Also in between, I'm very pleased that we had some engagement from the audience on the YouTube comments. And yeah, I would like to thank Johan, Victor here, and especially you, Vasily, for kind of giving us the opportunity to see your work in that format here. Thank you very much.
Thank you. It was a pleasure. It was absolutely a great conversation and discussion. Thank you.
A privilege.
Okay.
Thank you.
Then I will take down the YouTube stream now, and maybe you can just hang on for a short moment. Yeah. So. Good.